Hi, in this video we're gonna solve example 2.5. We're gonna draw the shear and moment diagrams. I'm gonna have to kind of start here in the middle because I was recording and I'm recording on my cell phone and then I got a message and it stops recording. So I apologize for that, but it'll help in that it'll make this video a lot quicker for you. So here we go. We wanted to draw the shear moment diagram for this shaft over here. It's got 2-point loads at the ends, the 300 newtons, 600 newtons, and a distributed load right down in the middle. So before we can do the shear moment diagrams, we need to figure out what the reaction forces are at A and B. When we look at this picture, we can see here, this is going to be a thrust bearing, and that's a journal bearing. However, in this problem, we don't have any side loading, so there's not going to be any need to develop a X component to the thrust. So that's going to go to 0. So we really just have a force in A and B. Since all the forces are trying to move the shaft down, I went ahead and assumed that the reaction forces at A and B are going to be up. So now to solve for A and B, simple statics, what I did over here is I did the sum of the moments at point A to solve for the force at B. Okay, so we had the 300 newtons, that's at half a meter. That's going to generate a counterclockwise or a positive moment. Next, I have the distributed load. And for the purpose of calculating the reaction forces, we can convert that into a point load over here. Since the distributed load is 1,200 newtons per every meter, and the span here from A to B is 1 meter, then it means that we can just simply use 1,200 newtons. So that is the force. It's going to be the place right at the centroid or half a meter away. And when we're summing moments at point A, this 1,200 Newton force is going to generate a clockwise moment or a negative one. Next, we have B in the opposite direction. So it's going to generate a positive moment. It's 1 meter away. And then finally, the 600 Newton force, it's 1.5 meters away, and it's going to generate a clockwise or a negative moment. We have one equation, one unknown. We can solve for B. We get a value for B of 1,350. Next, we sum the moment at point B here to solve for the reaction force at A. I always like to do that because I like to, as best I can, solve for the reaction forces independently and then use a third equation of equilibrium to check my work. So if you follow along this, you can pause it if you like, but here's the equation for the sum of the moments at point B. We were able to solve for a reaction force at A of 750. Then I went ahead and checked my work. I did some of the forces in the Y direction. So I got minus 300 plus 750 minus 1,200 plus 1,350 minus 600. And when I checked it, it equals 0. So that gave me confirmation that both A and B are correct. And it gave me okay to continue working on the shear moment diagram. So if you remember, when we're looking at the shear diagram, we're just looking at these arrows over here. Anytime you have a distributed load, right? Yes, we converted to point load to figure out the external or the reaction forces. But now these shear moment diagrams are giving us the internal loads, right? At any point along the span of the beam. So we have to get rid of that point load and just treat it as the original loading, which is distributed load. Anyway, so we start at one end. There's an arrow going down of 300, so we go down 300. There's no up and down arrows over here, so that force is going to stay constant until we get to the reaction at A. A was 750, so to minus 300, we add 750, and it's going to take us to this value of positive 450. So we're right here, and now we have this distributed load, and you can see that as we move every single point this way, there's an arrow pushing down, so it's going to bring us down. It's going to bring us down to this value. What is this value? Well, it's the total, right? It's a 1,200 newtons per meter times meter, which is 1,200. So basically from positive 450, we're going to subtract 1,200, and that takes us to minus 750. Over here, that's at point B. Now at point B, we also have this reaction force pushing us back up. B pushes with a force of 1,350. So minus 750 plus 13 1,350 is going to take us to a positive 600. So as we move along, there's no other loading until we get here. This is a negative 600. It's going to push us down and we're back to 0. And so this is a mark of a good shear diagram because we start at 0 and we end at 0. So that's a good thing. Next is from the information here, we're supposed to draw the moment diagram. We're following the graphical method, which means we're now going to look at the areas here to figure out the moments. Now we had this line going down, so it's going to be to our advantage that we figure out what is this, where does this line intersect here, the x-axis. And really what we're looking for is the base of this triangle because I want to figure out this area. Well, what I have over here is a line, right? We know the equation of a line is just is like so: y equals mx plus b, where m is the slope and b is the y-intercept. So what I'll try to figure out is the slope of this line. And if you remember, the slope is just rise over run. Or if we're using formulas, right, it's y2 minus y1 over x2 minus x1. So I'm going to call this point 1 and this one 2, right? So y2 is minus 750. Minus y1, which is a positive 450, divided by x2. This would be the distance, right? So this is 1.5 meters, and this is 0.5. And when we calculate it in the, put this in the calculator, we get a slope of minus 1,200, which should not be a surprise because we already know that the slope, the distributed value is going to give us the slope for that line. But I just wanted to remind you with this like completely graphical way. Anyways, so we're at minus 1,200 is going to be the slope. So we can go ahead and finish off the equation. We know the slope. Next is the intercept. And so what I did for this problem is I moved the origin to this point over here. So I'm gonna say this is the origin. That's my x and my y. And so that would make my y-intercept 450. And I think this is quicker than trying to kind of extend this slope over here and figure out what that point is going to be. Anyway, so we move the origin here. That would be the y-intercept, positive 450. And what we want to figure out is what is this value of x, right? When this equation is equal to 0, when the y value is 0. So we put y equals to 0 and we have the slope minus 1,200x plus 450. And we solve for x by moving the 450 to the other side, becomes negative, and dividing by minus 1,200. So isolate that x, and we get that x equals 0.375. So now we know that this point over here is 0.375 meters away from this reaction at A. So now armed with this information, we can go ahead and continue or move forward to drawing the moment diagram. So do you remember how we do the moment diagram? Yeah, so we're just looking at the areas over here. Right, so the moment always going to start at 0 over here, and then we're gonna figure out this area. Well, this is a square or rectangle, so the area of this guy is going to be the base, which is 0.5 meters, times the height, which in this case is negative 300. Multiply the 2, and we get minus 150. So that means we start at 0 and we have to get to minus 150. So let's say this one, 1, 2, 3. Here, because this is constant, this is going to tell us that it's going to be a straight line. So just like when we had like a uniform here, distributed load, that gives us a straight line or a constant slope. Here, this value is going to tell us that we need to do a straight line to right there. And this value again at this point is minus 150 Newton meters. That's my y values. So next, what am I going to do? I'm going to need to calculate what this area is. That's a triangle, right? So it's 1/2 the base times the height. So 0.5 for 1/2. The base, what is the base of this guy? We figured out to be 0.375. And what is the height? Well, it's this value over here times 450. And this gives us a value of 84.375. So this area right there is 84.375, right? But now I'm back at the moment. We were at a value of negative 150. And now we have this area. It's above the x-axis. So this is a positive one. So it means I need to add it, right? So I add 84.375. And the value that I get is minus 65.625. So that means that if I trace this point down, like so, when we reach this x of 0.375, this value has to be about 65 here. So this value is going to be minus 65.625. Next question is, how do we get there, right? Well, we know if we have distributed load, it's a line. What happens if we have a line, right? Or if slope equals x, this curve is going to be parabolic, or x squared. So it means I have two ways to get there, right? I can go kind of like this, or I can go and get down like that. So which one is it? Is it this way or this other way? So to get that answer, we look at this graphical method, right? And remember, the values of this curve is going to tell us the slope of this line. So over here we have about 450, and over here we have 0. So it means the slope goes from a very positive number all the way down to 0, right? So as we follow the curves, right, if I'm looking at this slope is almost 0, and then it goes very big. This other way, the slope is very positive and then goes down to 0. So what that means is the curve should be very high and then it levels off to 0. So here the slope is leveling off to 0. So we're at minus 65.625. And then what happens? We get this other area. It's negative, so we're going to subtract it, right? So this area over here is going to be, it's also a triangle. So the formula is going to be 1/2 or 0.5 times the base. So what is this base? Well, this base is this whole thing from here to here, if you remember, was 1 meter, but we already used up 0.375. So we're going to take 1 minus 0.375. That's going to give us this base over here, times the height. The height for this triangle is going to be negative 750, sorry. So it means this area is minus 234.375, right? And it's negative because it's below this x-axis. So it means to this value, now I'm going to subtract this one over here, 234.375. Okay, so negative 65.625 minus 234.375 takes me to minus 300. Okay, so if this was minus 150, another 200, 250, 300, more or less right there. So this is where we want to end up. The question arises again, right? We have a straight line. So the slope is here, the curve here is going to be parabolic. Is it going to be like this, or is it going to be kind of like that? So we got two options, right? This top one and this bottom one. Which one is it? Well, remember the values of this guy over here at each point is going to tell us the slope. So first, the slope is very close to 0, and then as we move away, the slope gets more and more negative, right? So which curve resembles that? So here we have very high slope. Remember, slopes like this are very high, and slopes that are horizontals are 0, right? So the ones that start with 0 or horizontals is this top curve. So this is more or less, I'm sorry if it's not a perfect parabolic, as this is by hand, but that's the curve that we need to pick, right? Because this one gives us right at the very end, when we get this point, very negative slope, very negative. Remember, positive, and this is negative like this. Anyways, so we're here at this point. This is minus 300. And now all we have is this other area over here. This is just a rectangle. So this area is the base, 0.5 times the height, which is 600. So, which basically means half of 600 or just 300. That's that area, right? So minus 300 plus 300, that's going to take us to 0. So that's very good news. We want both the shear and the moment to go to 0 at the ends because there's nothing there. And so now how do we get there? Well, we have here a constant, right? So it means we have to connect with a straight line. So remember the order of the curve. So if you have something like this, it means on the graph below, you're going to have linear. Whenever you have something linear, then it means that you're going to have something to the x squared. This is x and this is 0, right? If you had something that was already parabolic, now it's going to go cubic, and that's so on and so forth. In this class, this is probably as hard as we're going to get, and that's on purpose, right? They show you all of this in solids. We'll leave it there for the solids. And our job is, again, just to remember how to use the shear moment diagram. If we start over here with some like linearly varying distributed load, which is going to make it parabolic or x squared and then x cubed over here. Probably if we're going to do that, you don't want to use the graphic method anyways. The equations are going to be what you're going to need to do so you can figure out where the lines cross the 0 and all that kind of stuff. But in this class, you shouldn't need that. So we stick with examples and problems, even in exams. And this is as hard as you might get, just constant distributed loads. Anyway, so we did example 2.5. We drew the shear and moment diagrams. Why are we doing shear and moment diagrams in this class, right? This is all solids. Well, because when we're gonna design the machine components, one of them being shafts, we need to just watch out for that bending. And so to figure out where the maximum bending stress is, first we need to figure out where the maximum bending moment is. And so that's the tools that we're gonna use, the shear moment diagrams, to figure out the maximum bending. And you'll see in this next lecture how we use this value to then calculate bending stress. And again, that itself should not be anything new. It's from solids. But we'll just carry on. So hope you enjoyed it. Well, let me finish it off. Let me color it. Sorry, make it look pretty. There we go. Now we're done.